Welcome back to today's Explainer. Today we are diving straight into something absolutely foundational to network administration, and that is device management protocols. Specifically, we're going to unpack exactly how massive, sprawling networks diagnose their own pain and maintain a perfectly synchronized heartbeat. We're talking about two heavy hitters, Syslog and the Network Time Protocol, or NTP. Picture this for a second. You're managing a massive enterprise network. Deep in some dark, isolated server room, a single point of failure happens. A core router just unexpectedly dies. So if a router fails in the dark, how does it call for help? How do we, as the admins, ever actually find out about it before the help desk phones start literally ringing off the hook? Well, that's exactly the problem we're solving today. Here's our roadmap. We are slicing this right down the middle. First, how devices report issues, covering syslog, storage, message formats, and severity levels. And then, how they synchronize their internal clocks to make sense of all those reports using NTP, stratums, and redundancy. All right, kicking things off with part one, the network's nervous system. You can think of Syslog quite literally like the human body's nervous system. Instead of you having to go manually check the pulse of every single router or switch individually, they're designed to funnel all their anomaly signals, their pain signals, to one centralized brain. We call that a Syslog collector. These are basically fired and forget messages that travel over UDP port 514, constantly humming in the background, to alert us the second something isn't right. So let's talk about where those messages actually end up. Once a device generates a log, it needs a destination, right? By default, these messages will just flash directly onto your local console connection in real time. But if you want to look back at them later, they can sit temporarily in the device's RAM. That's buffered logging. Or for long-term safekeeping and aggregation, they get shipped off to that centralized external Syslog server we just talked about. Now, here is a massive gotcha, and you've got to remember this. If you are remoting into a device via SSH or Telnet, you are flying entirely blind by default. You won't see a single one of these pain signals pop up on your screen until you explicitly tell the device you want to see them. You do that by typing the terminal monitor command. It's a lifesaver. Okay, moving on to section 3, how we actually decode these messages once we see them. Let's be honest, at first glance, a raw, standardized Syslog message basically looks like alphabet soup. It's just a wall of text. But when you slice it up, it's actually incredibly structured. You can instantly spot the timestamp, the device ID, the facility, the severity level, and finally, the mnemonic and message text that details exactly what went down. People always mix up the facility and the mnemonic. So let's clear that up. The facility is the internal part of the router that's complaining, like the link or the line protocol. The mnemonic is the specific event that just occurred, like up, down. Just remember, the facility is who is complaining, and the mnemonic is what they just did. Up next, let's look at log severity levels, because frankly, not all pain signals are created equal. You absolutely have to know this 0 to 7 scale by heart. And it's totally counterintuitive. 0 is an emergency, meaning your network is essentially on fire and the system is unusable. As the number goes up, the severity actually goes down. It trickles all the way down to a 7, which is just highly granular debugging information, usually manually requested by an engineer. So a 0 means wake up at 2 a.m., and a 7 means it can definitely wait until Monday. Check out this actual raw log output. Right in the middle, you can spot that little 5. If we reference our scale, we instantly know that's a notification level event. It's a normal condition, but significant enough that we should definitely check why that interface just dropped. See how fast you can triage an issue once you know the code? All right, shifting gears completely for section 5. Let's talk about the cardiovascular heartbeat, keeping all this data synchronized, the Network Time Protocol, or NTP. NTP operates on UDP port 123. And why is this absolutely crucial? Because without NTP acting as the perfectly synchronized metronome across your entire infrastructure, trying to correlate a syslog error on one switch with a weird security event on a totally different router is literally impossible. If their clocks are off by even a few seconds, the sequence of events is totally lost, and your troubleshooting turns into a complete nightmare. Which brings us to our final section, how devices figure out what time it actually is using stratums and redundant time sources. NTP uses a hierarchy of accuracy called stratums. It's like a pyramid. At the very top, you have stratum 0. These are massive, master time sources like atomic nuclear clocks or GPS satellites. A server syncing directly to one of those is a stratum 1. A router syncing to that server is a stratum 2, and it just cascades down. The golden rule here is the lower the number, the more accurate the time. By the time you hit stratum 16, that time data is considered completely unusable.
But hey, what happens if your network gets isolated from the internet? Well, if an external clock isn't available, a Cisco router can actually use its own internal hardware as the reference clock by using the NTP master command. By default, it'll step up and provide that heartbeat at a stratum level of 8, which allows the rest of your local network to keep time relative to it.
And this right here is where you get a beautifully self-healing setup. The best practice is to prioritize highly accurate internet clocks, say a stratum 1 server, but you keep your router's internal clock waiting in the wings at an intentionally worse stratum, like 7. So your devices sync to the internet normally because it's the lowest stratum, but they seamlessly, automatically fall back to the internal clock if that outside connection ever drops. Oh, and pro tip for keeping this heartbeat alive, always tie your NTP updates to a loopback interface. Because a loopback is a logical interface rather than a physical cable that can get unplugged, it never physically goes down. So as long as the router itself has power and is functioning, your time services remain completely reachable. To wrap up today's explainer, I want to leave you with a pretty provocative thought about the deep security implications of time. Think about it. If a hacker manages to spoof your NTP server and manipulate your network's heartbeat, how could you ever trust the logs in your nervous system? The exact sequence of every security event, every login, every failed interface, it would all be scrambled. It really just shows how deeply interconnected these foundational protocols are. If the heartbeat is compromised, your entire network's reality is compromised. Thanks so much for hanging out with me today, and keep exploring these incredible protocols.